In part 9 of Quick Precalculus Review for Calculus, our focus is going to be using this computer program called Mathematica that you see here, and in particular a command called manipulate to help us make animations that ultimately will help us do a qualitative analysis of families of linear and exponential functions to compare and contrast them. We've been doing all our work in the context of two main examples, very common types of examples, population growth and car depreciation. Here's the population growth problem. If you haven't watched these videos yet, you might want to pause it and write this down and try to solve it. First try a linear model, then try an exponential model to estimate the population of Austin in the year 2020. Here were the answers that I got as approximate models. f1 of t is the linear function, 790 plus 31.7 times t. 790 is the initial population in the year 2010 in thousands of people. 31.7 is the yearly growth rate, 31.7 thousand people per year. That's constant, and this generates a graph that's a straight line. f2 of t is the exponential growth function. Again, the initial population, 790, is there. Now it gets multiplied by 1.03858 to the t power, which reflects the fact that on average the population of Austin, Texas is growing at 3.858% per year based on the two data points that we had. I used the table command in a couple spots to create list of points, one of which you see right here. I used ListPlot down here in this kind of way to create plots of those points, and then I can use a command called show to combine those plots with regular plots in the way I'm going to show you here right now. Inside this show command, I've got first of all a regular plot created with a Mathematica command plot of f1 and f2. I put those in there in a list separated by a comma. f1 ends up being red, f2 ends up being colored blue. I also have plot of points 1, which is the variable name for the first list of points that I plotted, with ListPlot above. You see plot of points 1 actually right here. Plot of points 2 is the graph that I created using ListPlot of the points that are on the exponential growth curve, and then I can enter this with the show and combine the graphs all in one. So big picture here, we have these two graphs. The red graph is the linear function, it's straight. The blue graph is the exponential growth. It's not straight, it's what's called concave up, and this is one of the main mathematical points of this video. Concave up, what does that mean? It means the slope of this graph keeps increasing. It keeps getting steeper and steeper in this case through positive slopes. In a sense, it looks like part of a smile. Okay, it's not straight, but it's always curving in one direction, a concave up direction. A concave down direction would look like part of a frown. It would look like this, how I'm drawing. But this is concave up. It looks like part of a smile. It ends up being above the linear growth at the very end and gives us a higher estimate for the population in the year 2020. Let's zoom in on this area here where t goes between 0 and 3 and p goes between, let's say, 700 and 900. I can change this plot range to zoom in there. And we see, once again, that the red graph is straight. The blue graph, being concave up, in this case, has to be below the red graph because these two graphs agree with the two data points. The two data points we had were 2010, where t was 0, and in 2013, where t was 3. In order for both graphs to go through those 2 points, the blue graph has to be underneath the red graph when you're doing this interpolation. But when you extrapolate past t equals 3, because the blue graph is concave up, it now gets above the red graph. Oops, change this plot range too. Let's change that 900 to 1200. Now t is going past 3. The blue graph, being concave up, has to go above the straight red graph after that point. Let's apply these same ideas in the context of the other example. Here's our car depreciation example. Now time equals 0 is the year 2013. When the car was worth $24,000, it goes down in value over time. The next year it's worth $21,000. Let's do the same kind of thing in this context. Here are our two models. This is the linear model. 24 is the initial value. Negative $3,000 per year is the slope, the rate of change. That graph is straight. G2 is an exponential decay function in this case. 24 again is the initial value of the car. Now we have times 0.875 to the t, a number less than 1 to the t power. That's exponential decay. The fact that we use 0.875 here means, one way of thinking of it is the value of the car the next year is 87.5% of the preceding year's value, and that'll work for any year. Another way of thinking of that is that the value goes down by about 12.5% every year. We use table and ListPlot once again to create these plots. I can change those 1s to 2 and then re-enter this to get those plots stored in these variable names. And I can once again use show to combine plots, a regular plot. Let's change this red to blue for the exponential decay. And I've got plot of points 1 and a plot of points 2. What kind of graph do we get? Here we go. It is a little odd sometimes Mathematica doesn't put the origin where it should be. I'll put axes origin in here, arrow 0, 0 to put the origin where it should be. There's our 2 graphs of the value of the car as functions of time. The red graph is linear, it's straight. The blue graph is exponential decay. It's not straight. In fact, it's still concave up. Okay? It's a decreasing function in this case, but it's still concave up. Still looks like part of a smile. More mathematically speaking, the slope of this graph is still increasing. It's negative, but those negative slopes are getting closer and closer to 0 as t increases. So the slopes are actually increasing, and that's why it's concave up. That's why it looks like part of a smile. If we zoom in, t going between 0 and 1 and v going between, oh, let's say 20 and 24, we'll see that the blue graph is indeed under the red graph when you interpolate between t equals 0 and t equals 1 where the graphs match. But then again, because the blue graph is ultimately concave up, once you get past where they match at t equals 1, the blue graph will be above the red graph. Need to change this to a 0. There we go. And so the exponential decay gives you a higher estimate for the value of the car than the linear decay would be. Again, I'm not thinking about questions of which model is more accurate. Conceivably, you could try both models and maybe even average the results to get your estimate for how much the car is depreciated. To end the video here, the last few minutes, we finally get to our main point, and that's to use the manipulate command to do a qualitative analysis. Okay, I did that before in a video a few videos ago. I used the manipulate command to do a qualitative analysis of graphs of families of linear functions as parameters change. What do I mean by parameters change? The parameters in this case are the slope, the y-intercept, m and b, that you see down here. I also allowed myself to change x by a certain amount, to start at a certain value of x and let delta x be the change in x, all within the animation. The plot that's created via show that combines a regular plot that you see here with, well, graphs of some lines that are created with graphics. I did show you this in the past. Are all within the show. The ending square bracket for the show is right here. If I highlight that, you see a little bit of a green tint to that, matching the green tint up here to match this square bracket. And the show goes embedded inside the manipulate command. Square bracket, it's an input for the manipulate command. The show goes up to this point. What comes after that point are the so-called animation parameters, in this case m, b, and delta x. You'll want to go back and watch a few videos ago if you want to understand that better. Let me just run the code in this case. What we get is a slider-enabled animation. We can change the slope, we can change the y-intercept, we can play it as a movie, a true animation, and see what happens as the slope changes. And we can change this delta x, which, well, it starts out at 0, so we didn't see anything, but once delta x is something positive, we see a right triangle in here, illustrating that rise over run stays constant for straight lines. The slope is constant because all these triangles are similar to each other. Let's see what happens if we do a basic animation with exponential functions. I'm going to copy and paste this code and then modify it. You have to know what you're doing here to an extent. I'm going to get rid of the graphic stuff. Let's see, does this square bracket match with the show? Yes, it does. I'm also going to get rid of the delta x animation parameter. I'm going to change the m animation parameter to an a. I'll keep the b as a b, though I'm only going to allow it to be positive values. What I'm going to be doing here is I'm thinking about animating an exponential function, a graph of an exponential function of the form a times b to the x. I guess I've used t for independent variables before, but here I'll use an x. That's my generic exponential function, a times b to the x. B has to be positive. You never really think about negative values for B. And B equals 1 is not really very interesting. It could be 1, but it's not interesting because it ends up being a horizontal line. A is almost always positive for applications as well. I can't really think of an application where an A for a straight exponential function like this could be negative, but I will allow myself to have negative values for A here, just so you can see what happens with the graph. This grid lines stuff, that just creates the grid lines that you saw in the last animation. Let's go ahead and enter this as is and let's see what happens. Okay, here is an exponential growth function. A times b to the x. A is the initial value at x equals 0. It's the vertical intercept. It plays the role of the vertical intercept. I can change A. The graph shifts up if A increases. It shifts down if A decreases, and in fact if A becomes negative, then the intercept is negative. If A is 0, that's not an interesting case either. That's the horizontal line y equals 0. Let's go back to letting A equal 2. B is the the formula again is A times b to the x. It's the growth factor, if you will. It's starting out at 2, which actually represents 100% growth per unit of time. For example, if x increases from 0 to 1, y increases from 2 to 4. It doubles. It increases by 100%. Likewise, if x increases from 1 to 2, y goes from 4 up to 8. It doubles again, grows by 100%. If b is, for example, 1.1, that would represent 10% growth per unit of x. The concavity is less so in a sense. Now as x increases by 1 unit, b is 1.1, so the growth is by 10%. When x is 0, y is 2. When x is 1, y has gone up by 10%. 10% of 2 is 0.2, so y goes up by 0.2 to 2.2 right there. Changing b affects that concavity, how steep the graph is and how quickly the slope changes. If b is between 0 and 1, that's an exponential decay graph. We get a graph like this. I will quickly show you this animation again in the next video, but for this video I'm going to end it right here.